Vector is going to be the topic in this last lesson in the first chapter of my brand new general physics playlist. And this is going to be foundational. So a lot of the true physics problems we're going to begin doing are going to be one-dimensional to start. But the moment they become two-dimensional, vectors are going to become super, super important. But before we get there, we've got to do a little bit of a trigonometry review because I really want you to understand vectors, not just kind of memorize some rules of how to break them into components and add them and stuff. I really want you to understand it. You're much more likely to own it that way. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Okay, so we're going to start this off with a little bit of a trigonometry review here, and a reminder of SOHCAHTOA here, and just a reminder what this stands for. So the SO here, so sine equals opposite over hypotenuse. So sine of an angle theta is equal to the opposite over the hypotenuse. Cosine equals the adjacent over the hypotenuse. And then TOA, the tangent of that angle is equal to the opposite over the adjacent. So that's SOHCAHTOA, and that's going to become relevant here in just a little bit. So we're going to go back and take a look at a right triangle. We're going to find out that looking at vectors and things of this sort, breaking up the components, adding them together, all this stuff is based on right triangles. And in those right triangles, the two legs of the triangle are always going to line up with the x-axis and the y-axis. Typically how we're going to make this work, and then you'll have some sort of hypotenuse associated with it as well. Now the right triangle I'm going to start with is this one right here. It's going to be a classic right triangle, and maybe you're already familiar. Maybe you're like, oh, Chad, I see it. It's a 3, 4, 5 right triangle. But if you don't, we can use the Pythagorean theorem to figure that out anyways. So if you recall, with a right triangle, we've got the Pythagorean theorem, a squared plus b squared equals c squared. And so in this case, that's going to be 3 squared plus 4 squared equals c squared. So 9 plus 16 equals c squared, or 25, and I'm writing this out all the way on purpose here, just to make it explicit here. So we'll take the square root of both sides there, and we can see that square root of 25 is indeed 5. And so this hypotenuse here is equal to 5, and indeed it is a 3, 4, 5 right triangle. It's a very convenient triangle to use for this example because it just makes the numbers easy, at least for the lengths of the sides. Now, what if, on the other hand, what if I was curious about what this angle was right here, or what this one was right here? Now, it's this one that I want, and we'll see why that is when we get to vectors specifically. But what might I use to figure that out? Well, it turns out, in knowing all three sides, I could use any of these trigonometric identities to figure that out. However, what if I said, before we figured out that part right there, using that Pythagorean theorem, what is that angle? And based on what I currently know, what would I use to figure that out? Well, I've got the opposite side, I've got the adjacent side, I don't have the hypotenuse, so how do I figure out angle? Well, in this case, because I've got the opposite side and the adjacent, but not the hypotenuse. Well, not the hypotenuse means I can't use sine and I can't use cosine, but I can use the tangent to figure it out. And so in this case, we're going to have tangent of, we'll call this theta, is equal to the opposite over the adjacent, so 4 over 3. And so then, to solve for theta, we take the inverse tangent of 4/3. All right, we'll definitely use our calculator to figure this out. Now, one thing to note, make sure the mode of your calculator is in degrees. I'm going to be doing all these calculations in degrees. That's principally what you're going to be doing in your course as well. There will be a couple places somewhere towards the end of first semester, maybe the beginning of second semester, where we do some things with radians. But for now, pretty much everything is going to be in degrees, and you want to make sure your mode of your calculator is adjusted accordingly. All right, so we're going to do the inverse tangent of 4/3 in parentheses there, and we're going to get 53.13 degrees. Okay, so that's that angle right there, 53.13 degrees. And if we wanted this one, well, we could go use one of our trigonometric identities, or we could just remember that The other two angles in a right triangle are complementary. They have to add up to 90 since that guy's 90 and they all three add up to 180. So we could just subtract 90 minus that to figure it out. But I don't care about that angle, it turns out. It's not the one I want that's relevant to what we're going to do here with vectors. I just want to, in principle, show that we could determine it if we needed to. All right, so now we've got this lovely angle. And so now I want to go and make some other assumptions. Let's kind of flip this on its head. So we've got this 3, 4, 5 right triangle. And now I want to say, well, what if I didn't know the 3 and the 4? What if I only knew the hypotenuse now? But I wanted to figure out what these two sides, what their magnitudes were. So how could I do that based on what I know and the trigonometric identities we have? So, well, a couple different ways. So if I look, I've got the hypotenuse and the angle. And I want to find the opposite side to the angle and the adjacent side to the angle. And you can quickly see that sine and cosine are going to be relevant here. So with sine angle, I've got the sine, I've got the angle. So I've got the hypotenuse, and I could use it to figure out that opposite side right there. So let's do that real quick. So on that opposite side, we're going to have the sine of our angle, which again in this case was 53.13 degrees, is equal to the opposite, which we want, over the hypotenuse, which in this case is 5. And so I don't know how to make that look more like an O than a 0, but it's an O for opposite. How about there? There we go. And that opposite side is going to equal now 5 times the sine of 53.13 degrees. All right, so let's multiply that out. So 5 times the sine of 53.13. Not worrying about sig figs right at the moment, FYI. We will worry about that for most true physics problem calculations, just not right here. And it comes out to 3.99999, i.e. 4. Just like we already knew it was a second ago. All right, now if I want this adjacent side right here, you might be like, well, Chad, you could get it from the Pythagorean. You're right, I could, but I don't want to. Again, I want to get it from that what was originally given in this part of the problem, just the hypotenuse and the angle. And now I want the adjacent side right here. And again, I've got the angle, I've got the hypotenuse, and I want to solve for that adjacent side right there. And so in this case, we're going to have cosine of 53.13 degrees is equal to the adjacent over the hypotenuse. So we'll move that 5 over again. And so 5 times the cosine 53.13 degrees is equal to our adjacent side. And once again, we'll take the time to do this out, but this should come out to 3. Kind of just a prediction. So 5 times the cosine of 53.13 is going to give me 3.00000 in a little bit, i.e. 3. Cool. And the big thing we want to demonstrate here is that if I've got the two sides, I can figure out this angle and the hypotenuse. If I've got the angle and the hypotenuse, I can go back and figure out the two sides. And the key is if I've got the two sides, well, getting the hypotenuse is just Pythagorean theorem, and getting the angle, we use the tangent since we had the opposite and the adjacent. But if I've got the hypotenuse and the angle, then I can use the sine function to get the opposite side, and I can use the cosine function to get the value of the adjacent side. And this is going to be crucial to when we break vectors into components and when we take those components and assemble them back up into vectors. And again, I'm not assuming you know what a vector is yet. We'll definitely talk about that in just a sec. Okay, so now let's talk a little bit about what a vector is. So, and it turns out we contrast two different terms here, vectors and scalars. And so a scalar is a term that only has magnitude and no direction, whereas a vector has both magnitude and direction. So I'll give you the difference here. And the most common example is speed versus velocity. And let's just say I was going down the highway doing 50 miles an hour. So let's, let me rewind that. Let's not even say going down the highway, because the highway is going to have a specific direction at a certain point in space. So let's just say I was moving in my car at 50 miles per hour. Okay, that's a speed and it's a scalar. You have no idea what direction I was heading. But if I told you that I was traveling in my car at 50 miles per hour due north, that both the magnitude, 50 miles per hour, and the direction due north, combined is what we call a vector. And it turns out velocity is a vector, whereas speed, which is just the magnitude, is a scalar. And we'll review that again when we encounter those back in chapter 2 again. But that's the difference between a vector and a scalar. A scalar is just pure magnitude. A vector is going to have both magnitude and direction. And so it turns out things like energy, it's just a scalar. There's no direction associated with an energy. But things like, we'll find out displacement, but velocity, acceleration, force, things of that sort are vector quantities. They have both magnitude and direction. That's going to be important throughout the course. And it turns out when you add vectors, that direction matters. So because if you add things that are, traveling, let's say, in opposite directions, you want to know what their resultant velocity is or something like that, or net velocity or net force when they're pushing in opposite directions or something like this, you've got to take into account that they are in opposite directions, and then oftentimes that means they're going to be canceling each other out rather than being additive. And what if they're not even in, the same plane in their motion? We got to deal with that. And that's where this vector stuff is going to become very significant. All right, so in principle, you got to know what the difference between a vector and a scalar is. Hopefully that's clear now. So we also got to talk about how we break vectors up into components and how we add vectors. And it's going to be crucial that we know how to break them up into components first. So a vector is written usually with an arrow on the Cartesian coordinate plane like this. And if a quantity is a vector, it's customary to put over that quantity an arrow, whether it's a half-headed arrow or a full-headed arrow, same diff. You'll see it both ways. But if you put a little arrow on top of that quantity, it signifies that it is a vector. It has both magnitude and a direction associated with it. And when we draw these on a Cartesian plane, typically the magnitude is going to be in some way, shape, or form proportional to how long the arrow we draw is. And so if I drew another vector on this with a shorter arrow, we assume it has a shorter magnitude. And then it's going to have some sort of direction associated with it. And that direction is usually defined relative to the x-axis. So typically it's this angle right here relative to the positive x-axis specifically that you're going to need and that you're going to use to identify that vector. Now, why can't I give you this angle right here relative to the positive y-axis? Well, I can. However, and you can do all sorts of different trigonometric stuff, it turns out, to figure out the components and all that stuff. However, I highly recommend that even if you're given the angle relative to the y-axis, that you look at that and be like, oh, yep, I'm not going to use that one. I'm actually going to know that it's complementary with the angle relative to the x-axis and subtract from 90 and find that one instead, and kind of get used to this process of using the angle specifically relative to the x-axis. It's customary kind of universally throughout all of physics. Could you do it with the angle relative to the y? You could. You're just going to find that you're going to have trouble understanding certain textbooks, like all of them, and how they set this up. So just kind of keep that in mind. That's why we're going the way we're going. All right, so it turns out a vector can be looked at as a combination of x and y components. And the way this works, we'll draw in those x and y components. So we often draw right on the x-axis an x component that takes me as far in the x direction as the very tip of that vector, and then another one in the y direction as well. And so this vector here, this line here, I should say, this arrow here represents the x component of the vector, and the red arrow here represents the y component of the vector. And if you notice, they, along with the vector itself, form a right triangle. And that's why we started off with our little trigonometry lesson. So because the vector itself, what we call the resultant vector, is going to be represented as the hypotenuse of a right triangle, and then the x component will be along the x-axis and be one of the legs. The y component will be along the y-axis and be one of the legs, and it forms a right triangle. And so the whole basis of dividing a vector up into its components, or assembling the components into a vector, is based on the same trigonometry we just reviewed. All right, so it turns out if you take a look at what we often define, we like to say that the x component, which we'll signify as ax, is equal to the absolute value. In this case, it turns out that represents the magnitude of the vector. Some people write a without the brackets here and stuff, but you'll see it both ways. And then times the cosine of the angle with respect to the x-axis. And we're going to be like, well, where does that come from? Well, great question. Where does that come from? We'll go back to SOHCAHTOA here, and the cosine of your angle is equal to adjacent over hypotenuse. And so if you look, if we keep using this terminology here, well, what we wanted was that adjacent side right there. And if we solve for that adjacent side, we can see it's equal to the hypotenuse times the cosine of the angle. Well, again, the hypotenuse is always the magnitude of what we call the resultant vector. So, and that's why it's showing up there, and that's why it's showing up right here. And then times the cosine of the angle gets you the value of that adjacent side, which we're calling the x component. Similarly, on the y component, we like to say that the y component of that vector equals the absolute value, i.e. the magnitude of the vector, times the sine of the angle with respect to the x-axis. Well, again, where does that come from? Well, that's going to come from the SO in SOHCAHTOA. And again, sine of an angle is equal to opposite over hypotenuse. And again, so we don't think that's a zero. So if I solve for that opposite side, it's going to equal the hypotenuse times the sine of the angle. Well, again, this opposite side is our y component. So, and your hypotenuse is the magnitude of the resultant vector. And then times the sine of the angle. And that's where we get that y component. Cool. Now here's the deal. Could you look and look up the SOHCAHTOA, look at all the relationships and assemble it all into place every time you look at this? You totally could. But you're going to want to get in the habit of being able to fast forward right here. So it's kind of like reading. I have two young sons that have been learning to read in the last couple of years. So we have things that are called sight words, and sight words are just words that are commonly going to show up in sentences that you want your sons to be able to recognize. Now, for larger words, they're going to have to sound those out phonetically, until they become words they're familiar with. Well, in this case, I'm just trying to get these to be, and actually I should have put a box around this whole equation here, but I'm trying to get these to be words you are familiar with. That way you don't have to phonetically sound them out when you encounter them. So, and again, this is a little bit dangerous here because I want you to get to the point where you're actually doing this without thinking, but not because you don't understand it, but because it's become elementary to you. So that's the idea. I want you to be able to look at a vector with its corresponding magnitude and its angle and be able to get the x component and the y component very quickly. Because it turns out breaking it up into x and y components will be imperative to being able to add vectors and things of the sort, any kind of vector math you might do. All right, so here we've got three different vectors. You can see the first one here is a vector equal to 18 meters, so it's got units of length. The next one's a vector of magnitude 18 meters per second. It's got units of velocity. And the last one's 18 meters per second squared. It's got units of acceleration. Now, the magnitude, minus the units anyways, is the same for all three vectors, but we can see that the directionality is different for all three. Now, what we want to do is find the x and y components for all three of these, and we want to use what we've taken home right here to kind of work that out. Now, the length is going to be the one that's going to be kind of the easiest to conceptualize, but we'll be able to apply it directly to what we see with velocity and acceleration as well, as we'll see. But we'll start with this one here, and if we take a look at those x and y components, again, we have an x component running right along here, we have a y component running right along here, and for that x component, that's the adjacent side relative to the angle with respect to the x-axis. If we didn't have the angle with respect to the x-axis, then we would find it. And so in this case, we're going to say that the x component is equal to the magnitude of the vector, 18 meters, times, in this case, it's again the adjacent angle, so cosine of 60 degrees. And that's going to get us our x component. We'll plug and chug that into the calculator. So 18 times cosine of 60, and we're going to get 9. Well, that's nice. So if you knew your geometric identities from way back in the day, you could have predicted this was going to be exactly half of the hypotenuse. So in this case, because cosine of 60 is 1/2, but well, no big deal. We worked it out. It came out anyways. If we do the y component now, and again, it's going to be equal to the magnitude of the vector times the sine of the angle this time, because we got the opposite side we're trying to find. So, and that's again 18 meters times the sine of 60. And this one you can't, do in your head. Sine of 60 is not a nice, lovely fraction like 1/2 the way the cosine of 60 was. But again, we'll let the calculator do the math for us. So 18 times the sine of 60. And that's going to get us 15.59. I'm just rounding to 15.6. Oh, and I should put the units on this. That's meters. And this is meters. And if we put them on the diagram, we've got 9 meters here. And we've got 15.6 meters here. Cool, so these are the vector components here. Now, if you take a look at this, what we've really got here is two ways to kind of take a look at this length vector. Originally, it was given that if you walk from the origin 18 meters, 60 degrees above the x-axis, you'll end up right here. And that's one way of describing it. So, but the x and y components are another way of describing exactly the same situation. So, with the x and y components, it says if you walk 9 meters in the positive x direction, followed by 15.6 meters in the positive y direction, overall net result, you end up in the same place. So it's kind of like if you're going to the grocery store and if you live in Phoenix, Arizona, like I do, the entire city is set up on a grid. So there are very few exceptions. So the whole thing's a grid. Streets run either north, south, or east, west. And so if you wanted to go to the grocery store from your house, well, if you could fly like a bird, you could go directly there. But the rest of us, we're going to drive there, are going to have to take streets that either run east-west or north-south to get there. So, but either description gets you there, right? So if I go 9 meters in the positive x, followed by 15.6 meters in the positive y, I end up right there. That's giving you kind of like the xy coordinates of a point. Whereas if I said go 18 meters at 60 degrees above the x-axis, that would be analogous to giving you the polar coordinates, if you remember your polar coordinates and stuff like this. Now, I'm not really going to talk about polar coordinates at all. I just wanted you to see, for those of you that are comfortable with it, who might be a little more intimately familiar with some pre-calc and calc, it is analogous to polar coordinates here when you've got the magnitude of the vector and its direction relative to that x-axis. Okay, but they're both ways of representing that same axis, whether you have the magnitude of the resultant vector, we call it, with its direction, or if you have the x and y components. And you've got to be able to convert from one to the other. And again, if you got the components, you can use the Pythagorean theorem to get the resultant vector's magnitude, and then use the inverse tangent to get the angle with respect to the x-axis. Or again, if you've got the resultant vector and the angle, we can use our lovely SOHCAHTOAs here, in this case sine and cosine, to get the x and y components magnitudes respectively. Okay, so that was the first quadrant. Now we've got a vector that's in the second quadrant here, and we have still got the angle relative to the nearest x-axis. But the thing I want to point out here is if we draw in the x and y component here, so there's our x component. And there's our y component. The thing I want to point out here is that the y component still points up in the positive y direction, but the x component's pointing to the left off in the negative x direction. And so before we even do the plug-in and chug-in here, we should recognize that the y component's positive and the x component's negative. So, and we'll see why that's important in just a second. All right, so let's calculate out those components. And in this case, if we say that the x component is equal to 18 meters per second, times, and in this case again, we've still got the reference angle in that second quadrant is still 60 degrees. And we could totally use that. So the problem is that if you always use the reference angle, which is always going to be between 0 and 90, well, then all your sines and cosines are going to come out positive. But in this case, you'd have to make the x component negative after the fact, just recognizing which quadrant it's in. And you can do that. And that's actually the way I learned it back in the day, 20 plus years ago. So, however, the other thing you can do is take and get that angle relative to the positive x-axis right there. And if you use that angle, the sines and the cosines will work out nicely every time. Now the tangent won't, but the sines and the cosines will. And so if we use 120 degrees here instead as our angle with respect to the x-axis, and so instead of putting in cosine of 60, we're going to put in cosine of 120 degrees, we'll find out that this x component is going to come out negative by default. I don't even have to remember that it's negative. Using the angle from the positive x-axis will generate whether it's positive or negative for me. All right, so in this case, we've got 18 times the cosine of 120 degrees, and it comes out to be -9 this time. The same thing for the y component. 18 meters per second, now times the sine. And again, I could use the 60 degrees, but again, it's going to give me the proper sine without me having to think about it if I use the angle with respect to the positive x-axis, the 120 degrees instead. Now here's the deal. Sine function is going to be positive whether we do the first quadrant or the second quadrant and things of this sort. So it turns out it's not going to make a difference here, but if it was in the third quadrant or fourth quadrant, it would make a difference, it turns out. So, but in this case, if we do that 18, in fact, we already know this is going to work out to be 15.6 meters, and it does indeed come out positive. And I should say 15.6 meters per second in this case. Cool, now these are velocity vectors. This deals with now the direction in which some object is traveling rather than some distance that was traveled. It's a direction and a speed at which something is traveling in this case, but it works the same way. We can see it's heading more in the y direction than it is in the x direction based on the magnitude of those x and y components. So, and in this case, it turns out it's heading 60 degrees above the negative x-axis or 120 degrees from that positive x-axis. All right, let's do one more. So we've done one in the first quadrant, we've done a vector in the second quadrant, now we're going to deal with a vector in the third quadrant and see it's going to work out similarly here. And if we break this up into x and y components and form a right triangle again, there's your x component. You see it's traveling in the negative x direction, or in this case it's got an acceleration in the negative x direction, but it's negative. And then the y component, we can also see is now in the negative y direction, so it should come out negative as well. And so the x and y components are both negative. Now, a couple things we should realize. If you were going to do this with a reference angle, that reference angle is always with respect to the x-axis. And so you'd actually want this angle right here, not the 30 degrees that was given. And if that angle is 30, then this is the complementary angle. These have to sum up to 90, so it'd be 60 degrees. But in this case, I'm saying, you know, you might even just go all the way around back to the positive x-axis and get the angle with respect to that positive x-axis. So here it's 90 plus 90 plus 60, or you could say it's 270 minus 30, and you're going to get 240 degrees. All right, so if we find our components now, we'll say that AX is equal to 18 meters per second squared times the cosine of 240 degrees. And once again, I know how this is going to work out. So in this case, notice it's the same triangle, same reference triangle in different quadrants. And that's why the x components and y components, their magnitudes are not changing. But again, if you're going to take the cosine of 240 degrees, it will come out to be a negative number. And in this case, again, -9. But now units of acceleration instead. And analogously with the y component, now with the sine of 240 degrees. So, and in this case, instead of being 15.6 meters per second, it's meters per second squared, and the sine of 240 is indeed a negative number. Cool, so had you used just the reference angle and said, oh, the reference angle is just that 60 degrees, you would have had to remember that, oh, but I need to make it negative in both cases since it's in that third quadrant. So, but again, if you use the reference angle of 240, the negatives will come out right out of your calculator for you. Okay, so now we've broken all three of these vectors up into x and y components. And the next step is now going to be, well, how do we add vectors? So, and that's a great question. So let's go take a look. All right, so now we're being asked to calculate the vector sum of these two vectors. Now, in this case, I've presented these two vectors to you on the study guide on two different sets of Cartesian coordinates here. So, but most likely they're going to be most likely presented on something like this, where they're put on the same Cartesian axis. Now, when you're doing this, you're asked to add these two vectors. We add them in what we call tip to tail fashion. And it doesn't matter which one you start with, but you've got to start with one of them. And I'm going to start with the one in black here first. Draw it from the origin. And again, that's 5 meters and an angle of 53.13 degrees. So, and then from tip to tail, it's tip. I'm now going to start the tail of that one and kind of transpose it right off over here. So this angle right here is 53.13 degrees. And then this angle right here is 22.62 degrees. Let's see if we can write that a little cleaner. All right. Cool. The resultant vector would be from the start, the origin, all the way to where that final resultant vector ended up. And that's ultimately how we diagram out a resultant vector. And I need to know its magnitude, and I also need to know its direction, its angle with respect to the x-axis. That's ultimately what we're being asked to find here when we're asked to find the vector sum of these two vectors. And the way you add two vectors is you break them up into components, and it's the components that you're going to actually add together, and we'll see why. All right, so for this first one here, we're going to have an x component and a y component, and this should look a little familiar with that 53.13 degrees. So, but we're going to have the x component, and I'll call it ax, equaling 5 meters times the cosine of 53.13 degrees. And again, this is where, I said you want to get to the point where this is something you've previously understood. It's become elementary, and so you can just kind of regurgitate it. So, but the x component is going to equal the magnitude of the resultant vector times the cosine of the angle with respect to the y-axis. And then the y component is going to equal, again, the magnitude of the vector times the sine of that same angle. Cool. But this, again, should look familiar because this x component, when you work it out, is going to be 3 meters, and the y component's going to be 4 meters. This was our 3, 4, 5 right triangle we kind of used as our trigonometry example, and we did for a reason. And it turns out our second one's actually going to be a famous right triangle as well. But we'll break it up into components in the same fashion. So ax is going to equal the magnitude, 13 meters, times the cosine of 22.62 degrees. And then the y component, again the magnitude, i.e. the hypotenuse, times the sine of 22.62 degrees. We'll let our calculator do the work here for us, but I know how this is going to work out. I chose the special right triangle this is coming out of. But we'll do 13 times the cosine of 22.62, and we're going to get 11.9999, i.e. 12, as the x component. And the y components, 13 times the sine of 22.62. And it's going to come out to 5.0000 and something, so essentially 5. And notice I am totally not worrying about sig figs here. I don't want to get lost in the weeds worrying about it. Again, on some serious problems, we'll definitely worry about it. But for now, let's not get lost on some crazy math or on the sig figs. Let's get the concept down. Okay, so if we see what's really going on here with our x and y components, and we kind of superimpose it right back over here. So for the first vector, the 5, we had an x component right here that was equal to 3 meters, and a y component right here that was equal to 4 meters. Okay. And then for the other vector in red, we had an x component that was equal to 12 meters, and we had a y component that was equal to 5 meters. Okay, and so if we go back one more time here, and all I want this time is actually that resultant vector we drew in blue. That's what we're looking for. Well, if you kind of look at what's going on here, we know what the x component is. It's this 3 meters right here plus this 12 meters right here. It's a total of 15 meters. We're just adding the components because that's the entire x distance of that resultant vector. And same thing in the y. We've got this 4 meters right here and then this 5 meters right here. And we can see that it is a total of 9 meters. And we've got a new right triangle now where the x component is 15 meters total, the y component is 9 meters total, and now I can use the Pythagorean theorem to get the hypotenuse, and I can use the tangent identity to get that angle with respect to the x-axis. But this is why when we go to add vectors, we break it apart into x and y components, and we add the x components together to get the new x component of our new resultant vector. And we add the y components together to get the new y component of our resultant vector. That's why that works. Now let's go ahead and do this. And so in this case, again, x component here is 15 meters. Y component's going to be 9 meters. And so let's find what that resultant is. And so in this case, Pythagorean theorem says 15 squared plus 9 squared is equal to 306. And that's our a squared plus b squared equals c squared. Let's write this out explicitly. So 15 squared plus 9 squared equals c squared. And again, that comes out to 306. So then we'll take the square root to find our hypotenuse. And it comes out, that's not the square root. Let's try that again. Square root of 306. All right, 17.49. Won't round it just yet. So, but that's going to have a magnitude 17.49, and again in this case meters. All right, and then we need an angle. And our angle here is again with respect to the positive x-axis. And so we got a couple different ways we can go about it now that we also know the hypotenuse, but in the classic way is just, if you've got the components, 15 and 9, just use that inverse tangent identity and be done with it. And so in this case, we're going to have the tangent theta equals opposite over adjacent, so 9 over 15. So theta is going to equal the inverse tangent of 9 over 15. And again, we'll let our calculator do the work for us here. Inverse tangent, 9 divided by 15. It's going to get us 30.96 degrees. Cool, and that's that angle right here, theta, 30.96 degrees. And so our resultant vector has a magnitude of 17.49 meters and a direction of 30.96 degrees above the positive x-axis. That is our resultant vector. And look at the power of this. So a couple different ways we could look at this. So if you want to know what this, how do you determine this resultant vector? Well, again, in this case, it's a distance, or it's a length, I should really say. A displacement we'll find out later. But it's got units of length in meters. And I can get from here to where I need to end up by traveling 17.49 meters in a direction that is 30.96 degrees above the horizontal. That's one way to pull this off. Or I could travel 3 meters in the positive x direction, followed by 12 meters in the positive x direction, followed by 4 meters in the positive y direction, followed by 5 meters in the positive y direction. Or I can scramble this up. I could travel 3 meters in the positive x, followed by 4 meters in the positive y, followed by 12 meters in the positive x, followed by 5 meters in the positive y, and I still would have ended up in the same place. Or I can travel 5 meters, so 5 meters at an angle of 53.13 degrees above the x-axis, or above the horizontal, followed by traveling 13 meters at an angle of 22.62 degrees above the positive x-axis, above the horizontal. And I'm still going to end up in the same place. So all of these are equivalent. And that, again, I just want to realize that breaking up a vector into its components is just another way of expressing that vector. And again, it's kind of like Cartesian coordinates versus polar coordinates. So, but cool, this is how you add vectors. If you wanted to subtract vectors, so the only difference you'd do is instead of, if again, these are the two vectors here, if I wanted to subtract this one minus this one, well then when I drew this out to do the resultant on this one right here, instead of drawing it out in this direction, I draw it exactly 180 degrees in the opposite direction when I start doing the tip to tail stuff. Cool, what does that mean in terms of your x and y components? Well, it means if I was doing this vector minus this vector, instead of doing 3 plus 12 for the x component, it would be 3 minus 12. And instead of 4 plus 5, it would be 4 minus 5. Well, what if I was doing the red vector minus the black vector? Well, then it'd be this one minus this one. And so it's kind of like just adding the negative of a vector, same thing as subtracting vectors. It turns out you can also multiply vectors by scalars. So if I want to take this, let's go back to the original. If I want to take this vector right here and you just want to multiply it by 3, okay, well that just means it gets 3 times longer. When you multiply a vector by a scalar, you get a vector that's just augmented by whatever scalar you multiplied it by. So if I multiply by 3, instead of being 5 meters, it would now be 15 meters, but in the exact same direction. What would that do to the components? It would also multiply them by 3 as well. And the x component would now be 9, and the y component would now be 12. And it would still be, form a triangle, if you will, a right triangle in the end that's analogous to a 3, 4, 5, or similar to a 3, 4, 5 right triangle, instead being a 9, 12, 15 right triangle. Cool, this is the deal with vectors. It takes some getting used to. You're gonna wanna do some practice. Fortunately, when we start doing real problems, we're gonna start with one-dimensional problems, and vectors is not going to be the hugest deal. But you need to get some practice. You need to get some practice breaking vectors up to components. You need to get some practice then assembling them back together. And then you need some practice adding vectors together. And we've done 2 here. In some problems, you might be adding 3 vectors together. And the key is you're just still going to break them all up into x components and y components, add all the x's together, add all the y together, and still come out with one overall resultant vector. Now, if you've liked this lesson and you found it helpful, then do me a favor and like this lesson and help me reach as broad an audience as possible. Happy studying.